In this video, we're going to talk about inverse functions. To talk about inverse functions, we have to talk about the definition of a function. And before we can talk about the definition of a function, we need to talk about what a relation is. A relation is a given list of points. So we see here the relation R is 3, 4, 5, 7, 7, 11, and 9, 4. Notice it's a list of coordinates, and remember coordinates are listed as x and y values. A function is a relation where the domain values are matched only with one element of the range. And so in my function here, I have the points 1, 2, 3, 4, 5, 6, and 7, 8. So notice when I map out my x values and my y values, each x value maps directly to one y value, making it a function. On a graph, this would be where we use our vertical line test or the pencil test, where we take the pencil over each point of our graph to see if the y values overlap. Function notation, in many of our courses and in this one, instead of writing y, we write f of x, and that's just using function notation. So now we're finding the inverse. So the inverse of a function or relation is found by switching the domain and range values. So if I'm given this function or relation here in this table, in order to find the inverse, I would need to switch my x and y values. After you do this, you want to check your y values and to check to see if your relation is actually a function. Since these are the only points we are given, it is a function, and we can write in function notation the inverse function. So notice in function notation the inverse is denoted by saying f raised to -1 of x. On a graph, the inverse of a function is that function reflected over the line y equals x. And that line, which I'm drawing here as a dotted line. And so if I wanted to find the inverse of this function f of x, I would reflect it over the line y equals x. Now before I call this inverse a function, I need to see if it is a function. Using the vertical line test, we see that it's not a function, and so I cannot use that function notation for inverse of a function. So now if we wanted to find the inverse algebraically, so given a function, we would, and if it's in function notation, you would rewrite it using x and y, so y equals x plus 3. You would need to switch x and y, and then solve for y. So to solve for y, I'm going to subtract 3 from both sides, and I get x minus 3 is equal to y. Now, before I say I'm done, we need to use function notation if this is a function. Since we know that x minus 3 will graph us a line and lines are functions, I can rewrite this to say the inverse function. I want to stress the importance of using function notation, but make sure that when we're using function notation, we're using it when our inverses are actually functions. So that is something to check for. So, say we are given two functions and asked to find if those two functions are inverses of each other. In order to check if functions are inverses, we composite them. And what it means to composite a function is if we have these two functions and we say f of, instead of saying f of x, we say f of g of x. This is where we're going to take our g of x function and substitute it in for x in our f of x function. So we're taking g and putting it into f. So when I'm writing the function f of x, instead of writing x, I'm going to write the equivalent expression of g of x. So instead of writing x, I'll write 2x plus 3, and then I'll finish out writing my f of x function. And so from here I can solve 2x plus 3 minus 3. My 3's will cancel and I'm left with 2x divided by 2. 2 divided by 2 is 1. And so I'm left with 1x. The definition of an inverse, if f of x and g of x are inverses, then f compose g of x, so the composite would be equal to x. In this example, when we took g and substituted it into x in our f of x, we solved and got x. We can say f of x and g of x are inverse functions.